In section 3.8, you will learn how to use Newton's method. And Newton's method is used to approximate the roots of a function. So for example, right here, this would be a root of this function. Well, hundreds of years ago, they didn't have scientific calculators where they could plug in numbers that had lots of decimal places and use it in a complicated function and crank out the next value. So Newton came up with this method where we start with a guess at x1 and then we use the tangent line to get x2. So if we look here, we have this point here where the coordinates would be x1 comma f of x1. If we follow the tangent line down, it hits the x-axis at this root, which is at x2, so the coordinates here would be x2 comma 0. Now we're going to tie this in with our knowledge of calculus, where the derivative gives us the slope of the tangent line. Now also remember from your algebra class that slope is found by doing y2 minus y1 over x2 minus x1. Now if derivative gives us slope of the tangent line, then we know that f prime at any particular x value, for example c, will equal the slope of the tangent line evaluated at x equals c. Now in this picture, let's look at a specific x value here of x1. So then that means f prime of x1 is going to equal the slope of the tangent line at x1. Well, we can find that slope because we have 2 points on that line. So y2 is right here, it's 0, minus y1, which in this case would be f of x1. That's over x2, which is x2, minus x1, which is x1. Now, we know who x1 is because we picked it. We know who f of x is because that's the given function. We know f of x1, so that means I also know this value because I can take x1, which I know what it is, plug it into the derivative, which I could find. So we know everything in this equation except for x2. So what we're going to do is solve for x2. So to do that, I will cross multiply up, and we have quantity x2 minus x1 multiplying f prime of x1 equals negative f of x1 on the right hand side. Next, I will divide both sides by this f prime of x1. So now we have that x2 minus x1 is equal to negative f of x1 over f prime of x1. Now all we have to do is add x1 to both sides, and we have that x2 is equal to x1 minus f of x1 over f prime of x1. And this turns out to be a formula that we can do many iterations of. Now because we know who x1 is, because we picked it, we plug that into the function, we know this value, we find the derivative, plug x1 into that, and we know that value, which means we can then do this calculation. So now we know who x2 is. Now that we know who x2 is, what we do is we drop down from x2 onto the function, and we will draw in the tangent line there. And we will call this point x3. So you can see we're getting closer and closer to the actual root. x2 was this far away. x3 is closer. It's only this far away. And now we can do the same formula for x3, and we can say that it's going to equal then x2 minus f of x2 over f prime of x2. And now we know who x3 is. We have that actual value, and we could put that into the function, use x3 to get this point on the function, and we could draw in the tangent line there. And you can see already we're getting very close to the actual root. x4 would be here, and we would find x4 by applying Newton's formula to x3. So we'd have x3 minus f of x3 over f prime of x3. And we can continue to do successive iterations of this so that the next iteration, call it xn plus 1, we just use the previous iteration, which would be xn minus f of xn over f prime of xn. And this is Newton's formula. So this brings us to Newton's method, which is used to approximate the roots of a function. To begin with, f must be differentiable on an open interval around c, where f of c is equal to 0. So remember, this is the root. Whenever the function is equal to 0, then that means x equals c is a root. Now what you do is pick a starting value, which we are going to call x1. And you pick that value because you think it is near the root c. Second, you will find a simplified formula for xn plus 1 equals xn minus f of xn over f prime of xn, and evaluate successive iterations of xn plus 1. So what that means is you're going to find x1, and then you'll find x2, and then you'll find x3, and so on. That's what they mean by successive iterations. These are the iterations, x1, x2, x3, etc. Now thirdly, you will stop when the absolute value of xn plus 1 minus xn is less than your margin of error. So all this is saying is that you're close enough to the value that you want to get to. The difference between your two iterations is so close that you're going to call it close enough. So then the question becomes, how do you pick a starting guess for x1? And you actually learned how to do this in your college algebra class, way before you knew anything about calculus. Step 1 is to plug in integer values for x. Step 2, look for a sign change in successive y values. Step 3, by the intermediate value theorem, a root exists between the two x values where the y values changed sign. So think about this for a second. Let's say you pick an x value here, let's call it a, and an x value here, you call it b. If the y value at a is positive and the y value at b is negative, that's what they're talking about when they say look for a sign change in successive y values. If you have a continuous function, and remember we learned if f is differentiable, we know it's going to be continuous. You know that somewhere it had to cross the x-axis on its way from x equals a to x equals b. So that's what you can use to sort of narrow your search for your starting value of x1. So here you will learn how to use Newton's method to find a root. In this example, we have to approximate a root of f of x equals x cubed plus x minus 3 using Newton's method with an accuracy of plus or minus 0.00001. So this tells you how close your answers have to be to each other before you stop. Now remember, the first thing we have to do is find a starting value for x1. And if you remember, we said the way to do that is to plug in integer values for x and then look for a sign change in successive y values. So here you just randomly start picking integer values because they're easy to plug in. So for example, I might try -1. If we put -1 in, we would have -1 plus -1, which is -2, minus 3 is -5. Then we could try 0, and f of 0 is -3. So in this case, there was not a sign change. Both of those are negative. We could try 1, and we would have 1 plus 1 is 2, minus 3 is -1. We could try 2, and we would get 8 plus 2 is 10, minus 3 is 7. So right here, this is the sign change that we were looking for. And since this is a continuous function, we know that the only way that it could get from a y value of -1 to a y value of 7 is if it passes through 0. So by the intermediate value theorem, there's a root in the interval 1 to 2. Remember, it's the x values where we talk about the interval. So in between x equals 1 and x equals 2, there has to be a root. Now if you think about what that would look like, at x equals 1, the y value was -1, and at x equals 2, the y value was 7. So all this is saying is that somewhere in between, it had to pass through 0 right there. And so, looking at this, you make your best guess and say, well, maybe we will choose x1 to equal 1.2, for example. Somebody else might have said 1.3. That's fine. Something near here. Next up, we're going to find a simplified formula for xn plus 1. Now to do that, we see we're going to need the function, which we have here, and we're going to need the derivative, which is here. So let's jot down. We can see that f prime of x is going to equal 3x squared plus 1. So now let's work on finding our simplified formula. We get x n plus 1 has to equal xn minus, now we're going to make a rational expression here where f of xn is in the top and f prime of xn is in the bottom. So if f of x is x cubed plus x minus 3, then f of xn is xn cubed plus xn minus 3. And if f prime of x is 3x squared plus 1, then f prime of xn is going to be 3xn squared plus 1. Now we are ready to simplify this formula, and then after we simplify it, we will use it to compute successive iterations. We would need to get a common denominator, and of course that denominator is going to be 3xn squared plus 1. Now we would have to multiply xn by 1 in the form of 3xn squared plus 1 over itself. So if we do that, that's going to become 3xn cubed plus xn. We just took this times this. Then we have the subtraction, and that subtraction has to distribute to all three terms. So we would have minus xn cubed minus xn and plus 3. Now let's simplify, and we get 3xn cubed minus xn cubed is 2xn cubed. We have a plus xn and a minus xn, which will cancel out, and the only term left is plus 3. And then in the denominator, we have 3xn squared plus 1. So this is what we mean when we say find a simplified formula for xn. Now we will use this formula and get successive iterations for the xn values. Remember, we said we are going to start with our original guess of letting x1 equal 1.2. Now, when you're using your calculator, I suggest strongly that you go ahead and store this into memory location A, and then we will do this calculation. So to use my calculator, I'm going to take that x1 value of 1.2 and I'm going to store that in memory location A. So if my cursor wasn't there, I would move my cursor under the A and then hit enter. So now that value is stored in A. Now I want to perform this calculation to find x2. So to do that, let's hit the parentheses, because notice that this numerator will have to be put in a set of parentheses. we have 2, and then memory variable a, which it's showing you what that value is, and then we have to take that to the third power and add 3, close the parentheses, so that is our numerator, divided by the entire denominator. So we will need to put that denominator into parentheses as well. So open with a left parenthesis, 3, and then I want memory variable a, and I want to square that, plus 1, close the parentheses, hit enter, and you can see that x2 has become 1.213533,835. And I'm going to store that into memory location B. So we come over here, hit store, put the cursor under the B, and hit enter. So now we have that stored there. Now what we want to find out is if the difference between x2 and x1 is within our accuracy that we said we had to have. And remember, the accuracy was 0.00001. So pretty easy to see that this and subtracting this isn't going to be that close, but what I will want you to do is do that calculation, and it's a really easy thing to do. Right now we have x2 in there, and we can just subtract x1, which was memory variable a, and hit enter, and we see that the difference is 0.013533835. Because this number is bigger than our accuracy, that means we are not accurate enough, so then that means we have to continue. So because this was greater than 0.00001, we keep going. So let's just say go. Okay, let's try to find x3 now. And what I want you to do now is pause the video and you try finding x3 on your own, and then once you have a value for x3, then restart the video to check your answer. But it's really important that you try this on your own to make sure you know how to use your calculator. So to find x3, what you can do very easily is I'm going to use my up cursor, and notice this is where I had the original calculation using memory variable a, which was x1. All I have to do now is cursor over, replace the memory variable a with memory variable b, and I have to do that in 2 places. So this a is going to turn into memory variable b, and now I can simply do that calculation. If I use the cursor, you can see the rest of it's there. Hit enter, and now you have that x3 is equal to 1.213411,673. And I'm going to store that into location C. So let's store, move the cursor over to C, and hit enter. Now we want to see if the difference between x2 and x3 is within our accuracy. Remember, we have x3 sitting right here, so let's just subtract x2, which was in memory variable b, hit enter, and remember that this is taking the absolute value. So even though this comes out to be a negative, we are going to write it as a positive, which is 0.000122162. Now this is still bigger than 0.00001, right? Because 0.00001, this is 12 times bigger. So that means we have to go still. So now we want to calculate x4. So we can use that technique where we arrow up, find that last calculation we did with letter B, which was our x2, and now we're going to cursor over and change that to memory variable C. Hit enter. Don't forget to do it everywhere. There's 2 spots we have to do it. We cursor over to the other B and put instead memory variable C. Then all we have to do is hit enter, and now we have 1.213411663. And let's store that in memory variable D. Now it's time to double check our accuracy between x3 and x4. So we can simply subtract the x4 that is on the screen right now, subtract away x3, which was in letter C. Don't forget that you're taking the absolute value of that difference, so it will be positive 0. And it looks like we have 1, 2, 3, 4, 5, 6, 7 zeros followed by a 1. 1, 2, 3, 4, 5, 6, 7 zeros followed by a 1, which clearly is less than our accuracy of 0.00001, so we stop. Now we have to answer the question, which was to approximate the root. So we will say that the root is that x is approximately equal to, now we don't give this whole entire number here because since we have an accuracy of 0.00001, that tells you to round the final answer to 5 decimal places. So let's look here. We have 1, 2, 3, 4, 5, which means we look at the 6th decimal place, and that tells the 1 to stay. So then our root is that x is approximately equal to 1.21341. Next, you will learn how to use Newton's method to find an intersection point. In this example, we have to approximate an intersection point with accuracy plus or minus 0.00001 for f of x equals x squared and g of x equals x plus 1. Now we have the graphs of these two functions over here. Of course, this blue one is x squared and the red one is x plus 1. And we see there's a couple of intersection points. We're just going to find one of them. So maybe we will go after this intersection point right here. And we can use the graph to get our initial guess for x1. If we drop down, we see that this, of course, is x equals 1. This is x equals 2. So maybe this, we could use about 1.7 for x1. If you were doing this on your own and you had elected to use 1.8 or 1.6, all those would have been fine. So let's let x1 equal 1.7. We need to have a starting point. Now, it's important to remember we are trying to find an intersection point, but Newton's method can only find roots. So what we need to do is to create a new function, and we'll call it h of x, so that h of x will have a root where these two functions intersect. So remember that h of x returns the y value of the new function, and we want the new function to equal 0 at the place that these two functions over here intersect. So what we can do is make a new function, h of x, and set it equal to f of x minus g of x. So think about what this means. You take the y value from f of x, which is the y value of x squared right here, and you subtract away the y value of g of x. Well, at the intersection point, they both have the same y value. So it makes sense that this function will equal 0 at the place where these two functions intersect. So h of x is going to equal x squared minus g of x. Now remember, we have to subtract that whole function. So if we are doing minus g of x, that would equal negative x minus 1. So we are subtracting x and subtracting 1. Now for Newton's formula, we know that we will also need h prime. So let's write that down. And that's a simple derivative. It's going to be 2x minus 1. So now we have to find a simplified formula for xn plus 1, and then we will use that formula to compute successive iterations, meaning x1, x2, x3, etc. So now we know our x sub n plus 1 is going to have to equal x sub n minus h of x sub n over h prime of x sub n. Remember, we have to use our new function because it will have a root at the intersection point of f of x and g of x. So this is going to equal xn minus h of xn goes in the numerator. So xn squared minus xn minus 1. And in the denominator, we have to put h prime of xn, which would be 2 times xn minus 1. Now we have to simplify. We know that the first thing we need is to get a common denominator, which will be 2xn minus 1. Then that means we will multiply this first term by 1 in the form of this denominator over itself. So when we take this times this, we're going to get 2xn squared minus xn Then we have to distribute this negative sign to all three terms of the second rational expression here, and we get minus xn squared plus xn and plus 1. We can simplify further, and now we have that xn plus 1 is going to equal, we have 2xn squared minus xn squared, so that leaves us with 1 xn squared. This minus xn and plus xn will cancel out, and we just have left plus 1. And then of course we bring down the denominator of 2xn minus 1. And this will be the simplified formula that we use to compute our successive iterations of xn. So remember we said that x1 was going to be 1.7. So let's go ahead and store that in memory location A. Now we can calculate x2 using Newton's formula. So we will need to put this numerator in a set of parentheses. So we start with the left parenthesis and we put memory variable A squared plus 1, close the set of parentheses, and divide by this denominator, which also needs to go in a set of parentheses. So we've got 2 memory variable A minus 1. Close your parentheses and hit enter. So we see that we've got 1.6208 and then 33333, and let's go ahead and store that in memory location B. Now let's look at the difference between x2 and x1, because our accuracy needs to be 0.00001. So we have x2 sitting in our calculator. We just need to subtract x1, which was memory variable A, and we can see the difference here. Remember that we are taking the absolute value, so we write it as a positive number, 0.079166667. And then we have to make a decision. Is this within our accuracy, or is it outside the accuracy? And since this value is greater than 0.00001, we know that tells us to go on to the next step and find x3. So remember the quick way now, because we've already calculated an xn value here, let's just cursor up and replace all the a's with b. So we cursor over and say memory variable b, and we have to put it in both places. Memory variable b, and then we can hit enter. And we've got that x3 is 1.618.037.485, and we're going to store that in memory location C. Now let's test to see if we are within our accuracy. So we have to subtract x3 minus x2, which was in memory location B, and then hit enter. And remember, we have absolute values here, so the difference is 0.002795,849. And that is still too big. It's bigger than our accuracy. So we have to go on and find x4. So now we can cursor back up, replace x2 with x3, so that means we have to put C in for the B's. Put it in both locations. Hit enter, and we see that we get 1.618033,989, and we're going to store that in memory location D. It's time to check our accuracy again. So we do x4, which is sitting in our display right now, minus x3, which is in C, and we hit enter, and we see that our accuracy is let's see, how many zeros? 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, and then 3496. And clearly that is going to be less than 0.00001. So now it's time to stop. Now we need to answer the question, which is to find the intersection point. We have the x value of the intersection point, and remember that this accuracy tells us to round to 5 decimal places. So when we look at our x value here, 1, 2, 3, 4, 5 decimal places, we use the 6th place, and because it's only a 3, it tells the 5th place to stay put. So the x value is going to be 1.61803, and now we need to determine the y value. Now we can either use f of x or g of x to find the y value, because both of them are going to have the same y value. F of x will return the same y value as g of x because that's exactly where they're intersecting. Now because we're using an x value of 1.61803, I don't really want to have to square that. It would be a lot easier to plug it into g of x and simply add 1. So when we come back down here, we see that our intersection point, if we add 1, the y value would just be 2.61803. So to use Newton's formula to find an intersection point, we had to create a new function by subtracting the two given functions so that our new function would equal 0, i.e. give us a root, where the two given functions intersect. Next, we are going to look at some examples where Newton's method fails to work. In this example, we have to apply Newton's method to f of x equals 2x cubed minus 6x squared plus 6x minus 1 using x1 is equal to 1. So first, let's get Newton's formula. We know that we will need F, and we will also need F prime. So let's go ahead and get F prime is equal to 6x squared minus 12x plus 6. We know x sub n plus 1 is going to equal x sub n minus f of xn over f prime of xn. So that's going to equal xn minus, if we take xn and plug it into f of x, we will get 2 times xn cubed minus 6 times xn squared plus 6 times xn minus 1. Then we have to take xn and plug it into f prime. So we would have 6xn squared minus 12xn plus 6. To simplify, we will need to get a common denominator. Now we know that denominator is going to be the only denominator we have. So 6xn squared minus 12xn plus 6. We know that we will have to multiply this first term times 1 in the form of this denominator over itself. So that's going to equal 6 times xn cubed minus 12xn squared plus 6xn. Then we will have to distribute this negative sign to all four terms in this second rational expression here. So we will have minus 2xn cubed plus 6xn squared minus 6xn plus 1. Simplifying, we get that xn plus 1 is going to equal, let's combine like terms. We have 6xn cubed minus 2xn cubed, so that's 4xn cubed. We have negative 12xn squared plus 6xn squared, so that's minus 6xn squared. Then we have 6xn, which will cancel with minus 6xn, and we just have plus 1 left. And then we have our denominator of 6xn squared minus 12xn plus 6. So now we need to calculate successive iterations of xn's. So let's go over here. We are told to use that x1 is equal to 1. So then to get x2, we just have to take this x1 and plug it in here. So the numerator would be 4 minus 6 is negative 2 plus 1 is negative 1. And in the denominator, when we plug in x1 is equal to 1, we get 6 minus 12 is negative 6 plus 6 is 0. And of course, this is undefined, and because of that, Newton's method fails. Now, to help you understand why this is, let's take a look at the graph of f of x, which is right here. We know in the denominator is f prime of xn. So when we're doing f prime of x1, when we look at this graph, you can see there is a horizontal tangent there. Because we get a 0, which will go in this denominator, we are unable to evaluate the xn. So this tangent line won't help us find the root, because remember, in Newton's method, we need the tangent line to intersect the x-axis somewhere, but a tangent line whose slope is 0 will never cross the x-axis. So physically, that's why Newton's method fails here. In this example, we have to apply Newton's method to f of x is the cube root of x using x1 is equal to 0.1 with an accuracy of plus or minus 0.00001. We know that xn plus 1 is going to equal xn minus f of xn over f prime of xn. Given that f of x is the cube root of x, which of course is x to the 1/3 power, then f prime of x is going to be 1/3 x to the negative 2/3, which we can write as 1 over 3 x to the 2/3. Then xn plus 1 is going to equal xn minus f of xn, which would be xn to the 1/3 power over f prime of xn, which would be 1 over 3 xn to the 2/3. Now let's simplify this. We get xn minus, here we have to take xn to the 1/3 power and multiply it times the reciprocal of the denominator, which would be 3 xn to the 2/3 power. So now we have xn minus 3xn, because xn to the 1/3 times xn to the 2/3 means you add those two exponents. 1/3 plus 2/3 is equal to 3/3, which is 1. So now we subtract. Xn minus 3xn is negative 2xn, and this is our simplified formula for xn plus 1. Pretty easy one. Now it's time to calculate values for the successive iterations of xn. And remember, we were told to use x1 is 0.1. Now we don't really need a calculator to do these, because all we have to do is take our current value of xn and take it times negative 2. So 0.1 times negative 2 is negative 0.2. Now when we subtract, we have negative 0.2 minus 0.1, that would be negative 0.3. Then we take its absolute value and we get positive 0.3. Now our accuracy was that we had to go to 0.00001. So this one's too big. So that tells us we have to go on and calculate x3. Now to find x3, all we have to do is take x2 and multiply times -2. So that becomes positive 0.4. And when we subtract 0.4 minus a negative 0.2, that becomes 0.6, which is greater than 0.00001, our accuracy. That tells us to keep going. And it's important to notice that not only is 0.6 too big for our accuracy, it's even bigger than the error that we had in the previous step. So now, if we calculate x4, we have to take x3, which is 0.4, multiply it times -2, and get negative 0.8. Subtracting, we have negative 0.8 minus 0.4. Well, that's going to be a negative 1.2. Take the absolute value, positive 1.2. That's greater than our desired accuracy. And once again, because it's too big, that would tell us to go on. However, we notice at this point that the error is getting worse and worse and worse. So what we notice is that Newton's does not converge here. So Newton's formula does not converge. And that means that Newton's method fails. So this is another example of how Newton's formula can fail because the error is getting worse as we go. Now physically what's happening, if we take a look at this graph again, at x1, if we find the slope of the tangent, that puts us here to x2, which was negative 0.2. Then we drop down to get x3, which was positive 0.4. And you can see we're actually farther away from this root than we were at x2. We go up to the graph, do the tangent line to x4, which was negative 0.8, and it just keeps getting farther and farther away. And the reason for that, as the curve goes out, the slope of the tangent is getting shallower and shallower, so by the time the tangent line hits the x-axis, it's really far away. And that means that Newton's method fails.